This video is going to be about a type of stereochemical isomer found in organic chemistry called a geometric isomer. Hopefully you've already seen the videos about the 5 types of isomers found in organic chemistry and can understand all of the structural isomers so that we can focus now on the 2 types of stereochemical ones, and specifically the geometric isomers we find in this video. In this video we're going to talk about isomers that are stereochemical isomers. Stereochemical isomers have bonds that are held in a specific orientation. What that means is that the attachments are all on the carbons to the same carbon, and the oxygens and hydrogens are all to the same places. But what's different is the way that they're held. This means that they have to have specific structures that cannot change. And the one that we're going to talk about in this case is going to be the geometric isomers. Geometric isomers must have a double bond in them. The double bond stops the rotation, so again it's held in a certain position so we can have those geometric isomers. Geometrical isomers often result from a double bond. Double bonds do not allow free rotation at the double bond. If I try to rotate something from the top to the bottom on a double bond, what will happen is that double bond will break, so I can't rotate freely. With single bonds, you could do that. In this class, we're going to focus on only the ones that work with double bonds. There are other ones, but we only look at the ones with double bonds in this class. To get an idea of what I mean by free rotation, take your 2 pointer fingers and point them towards each other, pointing both thumbs upward. Don't worry about the other fingers. Now, when we try to rotate this, you can rotate one of the thumbs towards you, and it can almost go to the downward position without ever hurting that single bond. The connection between the 2 index finger tips has not broken for me to go with both thumbs pointing up to one of them pointing downward. It might be a little uncomfortable because of your arms being attached to this, but we don't see that bond breaking. Now try it again. But take 2 fingers and point them towards each other, so your index finger and your middle finger, and you're going to have your thumb pointing upward again on both sides, and try to rotate it. What do you notice about what happens to the double bond? Notice how as you turn that thumb toward your body, that the double bond has to break. One of the bonds in the double bond breaks. That's what I mean by no free rotation around the double bond. Because there's no free rotation around the double bond, we can think of it as having a top half and a bottom half. And when we look at that, we're going to look to see where are the attachments placed. In our case, we'd be looking to see where the thumb is. And so we can see that if they are both on the top part or the bottom part, so they're on the same side, then we call those cis isomers. But if one is pointing up and one is pointing down, they're on opposite sides, we would call those trans isomers. Since these are isomers, that means that they are different compounds, and so they will be named differently. For example, this one would be called cis 2-butene, and this one would be called trans 2-butene. So the name is basically the same, but we're just changing the part that says if it's cis or trans. Let's identify whether each of these are cis or trans isomers. Then afterwards we'll give the name for each compound just for extra practice with naming. And finally we'll decide if there are any isomers that are the same, and which ones are actually isomers of each other. So some of these might have different carbon chains. That means they're not isomers of each other. They are still going to be called cis or trans isomers according to which one we've seen. You can pause the video while you try these, then restart it when you're done. Let's start with letter A. So notice that there are 2 things coming off of here. There are hydrogens, and then there are 2 carbon chains. We're going to focus on the carbon chains, and notice that they are both going the same direction, so this is a cis isomer. Now let's look at B. Again, we're looking at the carbon chain. We notice that one is pointing downward, one is pointing upward. That makes this a trans isomer. And we look at letter C, and we see that one is pointing up, one is pointing down. Again, we have a trans isomer. We look at letter D. We see that one hydrogen's up, one hydrogen's down, But again, we're focusing on the carbon. So we have one carbon down and the other carbon pointing up. That is a trans isomer. And letter E, we see one of the branches pointing to the left, the other one pointing to the right, and that is a trans isomer. And finally, letter F, we see that both branches are kind of pointing to the left and up, and so those are both going the same direction, and that one is a cis isomer. Now let's go back and name these. So with letter A, we see that there are 5 carbons in the main chain. So because it has a double bond, it's going to end with ene. There's 5 carbons, so it's pentene. What number is that double bond on? We see it on number 2. So this is a 2-pentene. And as we just mentioned, this is a cis double bond. So this is cis 2-pentene. Pause the video while you try the rest of these names, and I'll give you the names when you turn it back on. Let's start with B. So we have the ending ene. We have that there are 8 carbons. That makes this an octene, and that group is on number 1, 2, 3. So it's a 3-octene. Notice that there is a methyl group that goes in front of the number, so that is a methyl 3-octene, and the methyl group is on number 2, so the actual name is 2-methyl 3-octene. Now we have to still say if it's cis or trans. We see that this is trans, so then this one is going to be called trans 2-methyl 3-octene. All right, let's try letter C, and here we see that we have a double bond, so the ending is ene. There are 6 carbons in the main chain, so it's a hexene. We see that counting in either direction, we get the number 3 for the double bond, so this is a 3-hexene. And this one, when we look at those 2 branches, we see that it's trans, so we'd call this trans 3-hexene. Let's move on to letter D. The name will end with ene. There are 5 carbons, so it's a pentene. The double bond is on carbon number 2, so it's 2-pentene. And finally, we have to identify it as cis or trans, and this one is trans, so this is trans 2-pentene. And now letter E, we see that it has a double bond, so the ending is ene. There are 8 carbons in the main chain, so it is an octene. The double bond is on carbon number 3, so this is a 3-octene. And we see that it's trans, so this is trans 3-octene. And finally, letter F, where we see that we have a double bond, so it ends with ene. We have 6 carbons, so it's a hexene. That double bond is on carbon number 3, so it's a 3-hexene. And both of the carbon chains are pointing in the same direction, so that is a cis 3-hexene. Now let's look to see which of these are isomers of each other. So all of these are isomers, but we want to know which ones are isomers of each other, so in comparison to each other. In order to be geometric isomers, they have to have the same basic structure, which means they have to have the same chain length, attachments, and all of that, and only thing that is changing is which direction those double bonds are pointing. So let's look at A. It has 5 carbons, B has 8 carbons, C has 6 carbons, D has 5 carbons, E has 8 carbons, and F has 6 carbons. And so let's decide if these are isomers of each other. So A and D both have 5, B and E both have 8, and C and F both have 6. So let's look at A and D first. A and D are different structures because one is a cis structure and the other one's a trans structure. So these two are isomers. Now let's look at B and E. They both have 8 carbons in their main chain, but we do notice that in B there's an extra branch. So these are not the same molecular formula, therefore these are not isomers of each other. And let's look at letters C and F, and we see that one of them is trans, one of them is cis, and so that makes these two isomers of each other. For the following sets of compounds, we're going to identify which ones are the same compounds, which ones are isomers of each other, and which ones are not isomers of each other. As we identify the isomers, we're going to decide if they are positional isomers or geometric isomers. And the first step in this process will be to identify which ones have the same molecular formulas and which ones do not have the same molecular formula. So let's group them as ones with the same molecular formula. So for this step, notice that all of these are monounsaturated alkenes, and that means that if we count the number of carbons, we know that the formula will be CnH2n. So go ahead and write the formula for each of these. So pause the video and write the molecular formula for each of the following. That should look something like letter A. Okay, so let's look at letter B. B has 8 carbons. That means its formula is also C8H16. Now let's look at C. C also has 8 carbons, so its molecular formula will be C8H16. So as you go through these, hopefully you noticed that all but one of them had 8 carbons. So only H has a different formula. So A through I, except for H, has C8H16. Letter H has 9 carbons because one of them is a branch, and its formula will be C9H18. That means that H is not an isomer of the other ones. The next step is to see what position the double bond is in. So we're going to go ahead and group these by position. So put all the ones that are on position 1 in one area, 2 in another area, 3 in another area, 4 in another area, and so forth. Pause the video while you place them in the right areas. Notice that for the octenes, the only positions they can be in is 1, 2, or 3. After that, it starts counting the other direction. In this case, we don't see anything on position 1, so none of these are position 1, so these will be either position 2 or position 3. And in this case, we should say that A, E, and F are on position 2, and the rest of them are on position 3. So now we know that anything with A, E, and F is going to be a positional isomer to the rest of them, except for H. Now, focusing on just A, E, and F, let's decide if they are the same compound or geometric isomers. So to see that, we need to identify each of them as cis or trans isomers. Pause the video while you decide. You can place all of the cis isomers in one section and all of the trans isomers in the other. Okay, hopefully you could tell that all 3 of these are cis isomers, and that tells us that these are all 3 the same compound. There is no difference between them. Their name will all be cis-2-octene. Now let's look at all of the isomers of 3-octene. So again, place the ones that are cis on top, the ones that are trans at the bottom, and we will sort them out from there. And go ahead and pause the video while you do that. Okay, so you should have found that C, D, and I are all the same isomer. They are different from the others. They are all cis. B and G are each trans isomers, and they are the same as each other, but they are geometric isomers of C, D, and I. So when we name these, we know that C, D, and I are the same compound, and they are all cis-3-octene. B and G are the same compound, and they are both going to be named trans-3-octene. So to summarize, we know that H is not an isomer of any of the others because it has a different molecular formula. We know that there are positional isomers, and we know that there are some things that are the same. The things that are the same are A, E, and F. They are all the same compound, just drawn in different ways. We also know that C, D, and I are the cis isomers of 3-octene, and B and G are the trans isomers of 3-octene. We know that all of the ones that are the same, as you see the circle here, all the ones that are the same are going to be positional isomers of each other or geometric isomers. So A, E, and F are positional isomers of everything that is a 3-octene. So these are all 2-octenes, these are 3-octenes. And we know that C, D, and I are positional isomers of the one compound, B and G.